Bismillahirrahmanirrahim. Assalamu alaikum. Yesterday we started with the membrane separation process, and that was introduction about membrane separation. So today we have to continue with the same topic, membrane separation. So it's introduction, but before I start today's lecture, let me quickly revise the points which we have discussed yesterday. Actually we started with this, that when you look at the separation unit, they can be like categorized in four categories. So those include like separation through phase creation, through phase addition, through external force, and then final one was separation through some barrier. And in that we said that which commonly you see around that include like water filter. There are filters in vehicles, so in the lab when you go for filtration, so all those filter are actually providing you separation through some barrier. So membrane are also a barrier that can be as well as porous as well as non-porous, and they are used for various application in the industries. So when you look at the membrane, so any feed coming to the membrane is separated into two stream. One that pass through the membrane is called permeate, and one that stays on the surface of membrane, mean that didn't pass, that is called retentate. And then we said that initially membranes were slow, they were expensive, and they have various disadvantages, but with the passage of time various development took place in the membrane technology, and membrane became available for industrial use. And we also discussed the timeline that when membrane came into existence for various chemical industries, various applications. And at the end of the lecture I asked you to go through one table in which actually various based on various categorized industrial application were provided, like either they are being used as a reverse osmosis, microfiltration, ultrafiltration, there was gas permeation, and I think electrodialysis or maybe one other category. So based on that I asked you to look to go to the book. In table 14.1 all those industrial examples were provided. So now we have to continue from that specific point of industrial application. So in this lecture today I will discuss one industrial application in detail. So when and where membranes are used, and what is the advantage of membrane, what is its importance in that industrial specific process. So let's start with this process. So initially in this discussion I will introduce you with the process, that what is process, what is its importance, and from where did it came into existence, and then where actually membrane were introduced inside this process. So if you look at this that's actually production of benzene from toluene. This is one of the process which is used on large scale for and which involve membrane these days, but initially there were not membranes. So I just discussed its process, that why and when this process came into existence. So overall large scale membrane application is in the manufacturing of benzene and toluene, and at which stage in this process, as you know that this will be definitely a huge chemical plant in which there will be various processes, various steps. So actually there is one step where you have to separate hydrogen from methane inside this plant. So these membrane are used at this stage for separation of like hydrogen from methane. So let's look what is this process. Actually after World War II, in World War II toluene production increased to very high level. Why? Because toluene was being used for producing some explosive, and how it is used for explosive, actually it is used for production of trinitrotoluene, and this trinitrotoluene is used for production of various explosives. So after World War II, definitely refiners, all those petroleum refineries, they were looking for some other application, because after World War its usage for this trinitrotoluene reduced, but still toluene was being produced, and people started looking for various other uses of this toluene. and out of many uses, one was for production of benzene and xylene from this toluene. So where this toluene can be used for production of benzene as well as xylene in the same reaction, as well it was used for production of various polymers like for polyesters, like this is one example. So you can also look for various other example of uses of toluene, for production of various chemicals. So after when people looked that this can be used for production of benzene and xylene, so they started developing some process, and they came to know that this can be converted to benzene and xylene if we provide some catalyst as well as very high temperature of 950 degree Fahrenheit and pressure of above 500 psia. So at these conditions, what happens, actually this toluene is converted to benzene and xylene. Let's look at the reaction. So here you can see that actually when two xylene molecule toluene molecule are exposed to some catalyst, just look for catalyst if you are interested. It was not necessary here. So conditions actually are necessary. I will talk about this point, that why I have mentioned these. So this you can see that huge pressure and temperature are involved inside this system. So when two toluene molecule react with each other, so what happens, there actually disproportionation reaction takes place. What is disproportionation reaction? Actually you can see here toluene molecule, in this there is a ring, and then there is CH3 methyl group is attached to this. So this group, actually if I transfer this group from one toluene molecule to some other molecule, either that is toluene or any other, so if I just remove this from here and transfer it to other molecule, that reaction is called disproportionation reaction. So if I go for disproportionation, I am removing this methyl group, so what is left is, actually you can see here benzene ring is left. So we can get benzene, and that one methyl group which is detached from here, that can be connected, or that can be attached to other same toluene molecule, because there are two molecule out of those. From one, this is leaving and it is attached to the other molecule, so we are getting benzene at the same time, as well as there will be xylene. So where he has mentioned like xylene, at one random point, xylene has 3 isomers. So based on the position of this methyl group, that can be named as ortho, meta, or para xylene. So this is the reaction or one usage of toluene, in which toluene is used at high temperature and pressure in the presence of some catalyst to produce benzene and xylene. So during this reaction, as you can see, that temperature is very high. There is 950 degree Fahrenheit temperature is used. So at this high temperature, one reaction, maybe you are aware about it, that cracking of hydrocarbons takes place. Cracking means they are just broken down into the small pieces. So and in the presence of this much high heat, then finally what you get is all hydrogen is lost from those units, and you are left with the carbon, and that's called coke formation. Actually in this process, at this high temperature, coke formation takes place. And when coke formation takes place, what is disadvantage? Actually when your molecule is broken down into carbon and hydrogen, so it is like loss of your material, that is feed, as well as some product can also be converted, like this paraxylene, as well as benzene, as well as toluene. All these three actually are exposed to this cracking reaction. So due to this, they are lost, maybe your product is lost. At the same time, this coke or carbon which is released due to this reaction, that also is deposited on the surface of catalyst. So when catalyst surface is covered with this carbon, so those active sites of the catalyst will not be available for the reaction, and when they are not available, definitely reaction will become slow. There will be less production of benzene and paraxylene or other xylene isomer. So actually here the problem is like due to this carbon deposition, your product is formed in less amount. So we have to avoid this reaction, cracking reaction, and in order to avoid that coke formation, cracking reaction, what they do, they bring in hydrogen, and when you bring in hydrogen, so hydrogen is provided at some specific conditions, like there is large amount of hydrogen is provided in this reaction, but at partial pressure of 215 psia. I mean, if you look at the overall process pressure, so out of that hydrogen should have sufficiently high pressure, 215. You know that overall here the pressure is like, I think, 500 psi as he mentioned, so hydrogen is like 215 psi partial pressure of hydrogen inside system. So that's huge amount of hydrogen, and when you are providing this amount of hydrogen, that actually suppress this reaction of coke formation and fouling of catalyst or blocking of catalyst active sites, and this will help us to increase our production of benzene and xylene. But you know what happens as hydrogen comes inside system, so definitely hydrogen will not stay like just there, it will pass through. So it starts also reaction. Overall this is reaction in which there is no usage of hydrogen. Initially this was the reaction, but we brought in hydrogen to suppress some this cracking reaction, but that hydrogen starts some reaction. Actually hydrogen start reaction with this toluene, and it goes through hydrodealkylation reaction, and this produce benzene and methane inside the system. Due to this reaction, as you know, you can see that we are producing benzene, but at the same time we are producing undesired product, that is methane. So that's not our requirement here in this reaction, and that's due to this reaction definitely loss of your feed takes place. So although benzene is of use, but methane is of no use for this specific process, or you were not looking for methane at least. So in order to avoid this reaction, or somehow to reduce this reaction, what they did, they brought in not pure hydrogen. Hydrogen was brought along with some part of methane and ethane. So in order to avoid this reaction, because if methane will be present inside system, so that will suppress this reaction somehow. So maybe if you are interested, you can go to the chemistry of this reaction and can study in detail. With this overall, when we are bringing hydrogen that contains methane and ethane along with this, some reactions are taking place inside system. So overall, if we just look at this system, you know that you brought in toluene initially, and then you were producing benzene and xylene, but at the same time, when you bring in the hydrogen, so hydrogen produce somehow methane, but later we brought in hydrogen along with methane and ethane. So overall, if I look at the conditions or at the products coming from this reactor, so you can see that there will be hydrogen, there will be methane, there will be ethane, benzene produced in this reaction, there will be unreacted toluene, and then produce xylene isomers. These all will be available as a reactor effluent, or you can say these are the products coming out from reactor. Although all these are not our product, our products are benzene as well as xylene. Due to this, he is calling it as a reactor effluent, not reactor products. So this is the mixture of gases which will be coming out of this system at this high temperature and pressure at which reactor was operating. And one thing he mentioned there, that's like adiabatic reactor, in which there is no exchange of heat with the surrounding. So like this reaction will taking place at the conditions which were provided for the reaction. So overall, now when you have got all these products, or this reaction was taking place, this was all process. From here, if I just summarize, your purpose was to produce benzene and toluene, benzene and xylene from the toluene, but during this reaction, due to high temperature, cracking takes place, and in order to suppress that cracking reaction, we bring in the hydrogen inside system, so that actually reduce this cracking reaction and fouling of catalyst. But at the same time, when hydrogen comes in, hydrogen will not stay inactive, it will start reacting with the toluene, and due to this, what people looked at, it was producing methane at the same time. So in order to avoid this problem, hydrogen was introduced, not pure, it was included with like methane and ethane inside the system in order to avoid this side reaction which was taking place inside the system. So at the end, when you look at this various products coming out from this reactor in the form of gas effluent stream, we need to separate it, because at the end we will be looking for benzene and toluene, and also unreacted benzene and xylene, actually our products, and unreacted toluene we will be thinking about it to bring it back to the reactor, and also we have to separate these gases. So in order to do this separation, there are two actually ways or path which you can adopt. Actually, one was conventional one which was used earlier, not being used these days, but other process which involve membrane, which is the common one these days. But initially there was something which we call it conventional, in which actually conventional that didn't involve any membrane, but now we have some system which involve membrane. Right. So here let's look at this. This is the whole process provided to you. So let's look at this diagram overall. As I said that this method involve actually toluene, so in which you have to introduce the toluene inside system. So this is fresh toluene which is your feed. Coming to this reactor, so inside this reactor some reaction takes place and your products are produced, but you know that we have to brought the hydrogen in order to suppress this cracking reaction. So this is the hydrogen stream. So just this is combination of two, but just look that this hydrogen is coming to this system along with toluene, you are introducing it to the reactor. But at the same time some toluene which is recycled, actually from where it comes we will later look at this. So recycled toluene which was unreacted actually from the reactor, that is separated and we just bring it back to the reactor in order to avoid the loss of material. So this stream which is overall toluene and hydrogen with methane, ethane, that goes to the reactor which we said, and then in the reactor reaction takes place and reactor effluents, all that composition you have seen, that is coming out of this reactor. These effluent are those hydrogen, methane, ethane, there is toluene, benzene and xylene, these will be present here. So now when you come to this point up to here, we have discussed that they are produced, but now after production we have to separate them. The last point which I have discussed, that there are actually two systems which you have to use. So this is the one common one, that is process without membranes, which we are looking at this because this didn't contain any membrane. I will explain it in detail here. Then we will look at the other process which involve membrane actually. So overall in this process, now when you have these reactor effluents, they will be at high temperature of 900 degree Fahrenheit, 950 at which this was operating, and then there is also huge pressure. So what you can do, all they are coming in the form of now vapors, gas in the form of vapor or gas. So what we can do here, we can separate these gases from each other with the help of some separating units. So this is one common or very simple separation unit, that is called flash air, that's flash drum. Actually this is simple vessel in which due to density difference vapor and liquid are separated. So what are those vapor and liquid? First of all, here when they are leaving from the reactor, they all are vapor, they are in the form of gas and vapor. So we have to separate them. What we can do, what do you think, how we can separate them? As you can see from this at least, that there is vapor and liquid. So some of that can be converted to the liquid and other in the form of vapor. So what do you think, how we can do? So if we just reduce their temperature, so what will happen with this temperature and pressure, and as well as if we reduce the pressure, so what you can do, you can have heavier component, they will be condensed, they will become liquid. So from here at this point you can just install some cooling unit like heat exchanger can be installed, which reduce the temperature of this effluent coming from this reactor, and that is not shown here, but that can be used. So through this, when this effluent will pass through, it will cool down, its temperature will decrease as well as pressure somehow decreases, and when you bring it to the flash vessel, so due to density difference, vapor will move to the top and liquid will move to the bottom, and they will get separated. So now look here how you can cool it. What will be the cooling media? overall you see that here there is our feed which is coming to this reactor, and definitely this feed needs some heating, because you have to meet the condition of the reactor, that is 950 degree Fahrenheit. So in order to do that, what we can do, we can just exchange the heat of these product with the feed. Mean this is one way to do this, economically, like you can save your energy in the system. Otherwise you have to externally like heat your feed, and also you have to extract heat from here in the form of, maybe you can use water, but the better way is to cool this product with the help of feed. So this overall reduction in temperature will take place, and some of the component are condensed at this temperature and pressure, while other leave as a vapor. So overall, when they are separated inside this flash drum, you can see that this is separation. Before I come here, okay, just let's look at these lines here. Reactor effluent is cooled and partially condensed. Partially condensed mean some part of that is condensed. We are not condensing all, we are just condensing some, and some will stay in the form of vapor. So we will look at that which are condensed and which are not condensed. So at 100 degree Fahrenheit and a pressure of 465 psi, this can be like these are the condition at which we are operating this. So at these condition, a good separation between C2H6 and C6H6 is achieved in the flash drum. He has mentioned only two chemicals, as I have talked about this, that we have more than two, where there are 6-7 present inside system. But here he has actually provided us one light key and one heavy key. In the start of this semester, when we were talking about introduction to separation process, in the start first chapter, so there we have talked about this, that there is something called heavy key and lighter key. Actually a lighter key, or sorry, light key, that is one component which we consider that is light, and all those components lighter than this component will be considered or will go to the vapor side. Suppose this is light one, I consider it, suppose if it go to the vapor, so all other which are lighter than this will go to the that stream, that is in the stream in which this component is going. Suppose we just consider that this is ethane and it goes to the vapor side, we just don't condense it. So all those which are lighter than this, definitely they will also be staying in the form of vapor. So here in this system, your system, actually it will contain hydrogen as well as methane and ethane, because this we have considered that this is the light key, and all lighter than this will go to the same stream of vapor. And on the other hand, you can see that that is a heavy key, and that is your benzene. So toluene, there is toluene in the system as well as xylene, so they are heavier than this, so they will be staying inside the liquid. So this is our heavy key, and all components which are heavier than this heavy key, they will be going to this stream of liquid, flash liquid. So they are aromatics, and they are combination of like benzene, toluene and xylene, they will be present inside this system. So this is the overall process up to here, that this separation takes place. Now you will be thinking about this, that like this aromatic, that is again mixture, definitely you will go to some other separation unit, like either benzene, this separation of benzene and xylene we are looking for, as well as we are looking for like separation of toluene. So that can be so overall you will be thinking that these aromatic chemical, that's mixture of benzene, toluene and xylene, that can be separated like either in distillation or absorption, liquid extraction. Anyways, at the end you get separated your recycled toluene, and then you recycle it after separation of toluene. So this separation takes place and you get your product like benzene, paraxylene, and as well you will get toluene separated, that will come to the reactor. But the major point here, which is like flash vapor, that this is one mixture. So what we can do here, as you know that we have to introduce the hydrogen to the system in order to avoid this coke formation reaction. So what you can do, just consider for 1 minute like there is no part, this stream is missing here. So what you can do, you can bring all this stuff, hydrogen, methane and ethane, back to the reactor. So here you can see that I mean this is recycled hydrogen stream we just consider for a minute, and there is makeup hydrogen that's taking place overall. Mean makeup hydrogen, why we are bringing makeup, because some of the hydrogen we just consider, for example, that there is no purge, all hydrogen which went out of reactor is coming back, but you know that inside reactor there is somehow usage of hydrogen in the side reaction, so we have to bring some in order to, you can see that in order to meet that partial pressure of hydrogen, actually we have to give this makeup hydrogen. Makeup hydrogen mean that hydrogen is used to make up the deficiency, because some hydrogen which is used inside reactor, so that will not be available here. So in order to meet the partial pressure of the hydrogen which he has mentioned, so in order to meet that condition, so you have to introduce some fresh hydrogen from here. So overall, but in this system what will happen, as I asked you to just suppose that we are not purging anything. Purge mean anything which is just leaving from this system as a gas stream in order to avoid the build up. How it builds up, suppose we are not purging anything, so what will happen, this hydrogen, methane and ethane will be part of this stream. They will be coming to the system, they will pass through all this reactor, then effluent, flashing and so on, and with the passage of time, mean their amount will keep on increasing inside the system, because some hydrogen is produced inside, sorry, CH4 is produced inside the reactor as a side reaction. Mean you can't 100% eliminate them, mean somehow you can reduce, but still it will be producing. So what happens, what is disadvantage, because when you are bringing them again and again inside the system, so maybe you have to heat this in order to meet the requirement of reactor. Definitely you will be just wasting your heat to heat these chemicals as well. I mean when now you are going for cooling, here you will be just cooling them, in there is no advantage to you, and then flashing and overall mean this will be taking place. So in order to avoid this problem, mean they just purge some amount. Purge mean some amount of this gas or vapor leaving from this system is just mean taken away in order to avoid this build up of these non-usable inside the system. So when you are just mean purging some, so definitely you have to make up, mean because purging will not only take place of methane and ethane, there will be hydrogen part of this purge. So what is disadvantage at the end of the day, actually mean when you are purging, hydrogen is also going in this stream, so you are losing the hydrogen, and hydrogen when you are just mean you were losing the hydrogen, you have to do more makeup, and this was increasing the cost of the system. This was a conventional method which was without membrane, because what you can see here, there is no membrane inside system, and where we can install membrane, by the way, can you think about it? This point where you are just separating our flash vapor, they contain majorly hydrogen and methane, and some part of ethane is there. So if we just install some separating unit here at this point, after flash vapor are separated from flash tank, you just bring it to like some separation unit, and that actually if that separation unit can separate hydrogen and methane and ethane, actually your purpose is to separate hydrogen from these two other chemicals, so that will be beneficial for us. So all other techniques before membranes, they were not good for this, like distillation, absorption, stripping, like as well as there is LLE or other techniques, they were not good for this separation. Just if you are interested, just look for this, that why hydrogen and CH4 separation is difficult using all other techniques which you know without membranes actually. So then after some time there came into existence one method that involved membrane. Overall this diagram is similar as we have discussed previously at actually only one point. When flash vapor are leaving the system, flash vessel, you can have some separating unit here. They introduced actually in 1979, this came into existence. This process was used first time in the industry, that membranes were installed, and flash vapor which were leaving the flash vessel, they were passed through some membrane modules, and through those membrane modules then hydrogen was separated from methane and ethane. Let's quickly look at this system. Overall this system is same, like you are bringing fresh toluene and you are mixing it with the hydrogen stream. as well there is some recycled toluene, and they enter to the reactor conditions are same, which we have already talked about, in 950 degree Fahrenheit and 500 psi pressure. Inside the reactor, your main reaction of toluene conversion to benzene as well as xylene takes place, and some side reaction takes place, and your reactor effluent, that's also the main same stuff which you know there will be hydrogen, methane, ethane, benzene, toluene and xylene, and then as we said, you have to reduce the temperature, you have to cool them down, and overall flashing takes place inside this vessel, their separation takes place. So flash vapor composition is same as in the last slide, that is hydrogen, methane and some amount of ethane. Majorly there are hydrogen and methane, and there is some amount of ethane, but as well as you will have some other lighter, they will also be heavier. As we said that they are more or less condensed, but not 100%. There will be very small traces amount of benzene, toluene and xylene part of this. As well there is flash liquid, that is majorly those heavier hydrocarbon, and very small amount of this like ethane can also be present there. Then these S02, S05, S24, S08, these are the stream numbers. Actually in next slide you are provided with the material balance of each stream, that what is composition of each stream. We will look at few of those, like here S02, you know this is pure toluene, so there should be pure toluene, its flow rate actually is given. So for all these stream up to here we have already talked about this, and in the old conventional system, after this stream we purged some of the amount, while other was just recycled back to the system. But in this membrane was introduced, and that membrane has this tendency to separate methane from hydrogen. So that membrane is actually formed of aromatic polyamide polymer. This is its material of construction, polyamide polymer, and its thickness is only 0.3 micrometer, 0.3 micron, very thick, very thin it will be, like its thickness is very small, and that's non-porous membrane that is used here, and that has selectivity for hydrogen. What does this mean? Yesterday we talked about this selective membrane should be selective for some of the components, so it allows hydrogen to pass through through this system. When you are introducing your feed, that hydrogen will pass through, so hydrogen will be named as permeate or retentate. What do you think? It is permeate, so that pass through the membrane is named as permeate. So permeate, it will pass through membrane. As well some components, some part of this hydrogen as well as methane and ethane will leave from this system as retentate. They are rejected from the membrane, they didn't pass through the membrane. Rejected mean so they will be leaving from this system here as a purge stream. So overall you can see that this hydrogen flash vapor stream that leave flash tank, that is separated into 4 parallel units. Actually I will talk about this point later on in this lecture, that this is one of the disadvantage of membrane, that you have to install parallel units, and why we have to install, we will look at this. So overall these 4 parallel units, we are providing flash vapor of same composition to them, and overall here separation will take place, and you will get hydrogen as a permeate, and all other leave as a retentate. They leave from the system and this S14 recycled hydrogen, that will contain some small amount of all other components, because membrane are not 100% selective. They will also allow some other components to pass through. But one thing here I want to tell you is this, you can see this is 0.3 micrometer. Can you imagine? That's 10 to the power minus 6, 0.3 into 10 to the minus 6 meter, and just look for this in maybe even centimeter or millimeter, or overall this is very thin membrane. So can it extend with very high pressure? From this flash vessel there is pressure of 465 psia, so this stream will be available at this high pressure. So can you imagine that this very thin sheet will bear this pressure? No. Due to this we have to support this membrane, which is active layer actually, which is separating hydrogen from methane and other components, that is supported on some porous sport, and that porous sport is also most of the time they are polymeric component, but they are porous, they contain large pore, they are just being used as a sport, they are not like working as a somehow separation unit or active layer means layer through which separation takes place. So that is non-porous, you can see here that's non-porous. So later we have to talk about these membrane porous and non-porous in detail in next week, so you will get more better idea, but that top layer is non-porous and other support is porous one. So here you can see this one like this. Overall you can see that this contains 3 layers. Top layer is active layer and that is polyamide layer. In this actually major separation takes place. Then there are some sports, these are also polymers, but they are being used as a sport to bear high pressure of 465 or 450 psia here. So through this top layer hydrogen will pass through, all other will be rejected. Then later after passing through the top layer, hydrogen can easily go through all these 2 layers because they are just porous, they will not hinder hydrogen to pass through, hydrogen will quickly go through the system. So you can just think about it like suppose we are going for filtration inside lab, and you know that you have filter paper. So how do you sport filter paper? You place filter paper on a funnel. When funnel is acting here as a sport, because if you didn't place it on some sport, so if you just pour the liquid and that liquid will damage it, or that will just flow away from that filter paper. So in order to produce like some module inside, filtration will take place and you place at some sport. So these down layers here also acting as a sport for top layer, active layer. They are not participating in separation, they are just acting as a sport. So overall this is the construction of this membrane used here. Don't need to go in much detail. If just you should remember that there is one active layer and then there are some sport layers here just for the sport to bear high pressure. So overall when you look at this system, actually in this system at the end of the day, you know that you have like somehow hydrogen recovery of 90%. What does this mean? That like he has mentioned that recovery of hydrogen in the permeate is 90%. Suppose if you look at the amount of hydrogen inside the system at the inlet and at the outlet, overall 90% of hydrogen is recovered and that is recycled, only 10% is lost. Maybe you will be thinking that this is still huge loss of 10%, but if you compare it to the purge system and the old system when there was no membrane, so this was very much as compared to this, that was high. So with the help of this membrane system, definitely we are recovering more hydrogen along with small amount of methane, and that is recycled. So this will save actually the cost of makeup, as well as you know that in the purge system when you were releasing the hydrogen, but same time you were also spending on the heating and cooling and compressing of gases, methane and ethane present inside the system. So when you compare all these advantages, definitely this system is more effective as compared to the old system. And that's one example of industrial use of membrane in which you are using the membranes. So that's all about this system, this one industrial example in which how membrane is being used and how it is advantageous for us. So based on this you can see overall, yes, as I talked to you, that there are these are streams. Suppose if you remember S02 was ethane toluene entering to the system, so you know this S02. So S02 here you can see that its composition is overall toluene, that is 1069.4, and its unit is pound mole per hour. So its flow rate is given in the pound mole, and its total overall like at the end of each stream total is given, because this is only one component, so its composition is given here. And S14, you remember that S14 is like this hydrogen which is recycled to the system. So its composition, if we look at this S14, this is here given here, like it contains only hydrogen and methane. As well, you can look at the other. Suppose if you are interested, like S8, which is leaving the reactor, so its composition, you know that all were present in this stream. So overall you can see their amounts are given here, I mean, in all these streams. So this is all about this system, in which your purpose was produce benzene and xylene from toluene, but you introduce hydrogen, and then later you have to there was a need to separate hydrogen from methane. So if you remember the point where from where I started this lecture, that mean inside production of inside this plant in which production of benzene takes place from toluene, there is some point where you have to separate hydrogen from your methane. So this is the point where you are separating hydrogen from the methane, and that's helpful for us. That is improving the efficiency, or overall I should say production of this process, as well as that's helping us to save the money. Based on all this stuff which we have discussed so far, the membranes can be used on industrial scale, and they are being used on industrial scale. Actually, with the passage of time, there are few advantages of membrane, because if you remember yesterday I told you that membrane were suffering with various problem, that was high cost as well as their low selectivity for some specific component, and some other as compared to other separation techniques. But with the passage of time, membrane material have become more efficient. They can give good selectivity, as well as their module. This module the way in which they are arranged or they are used. So that has improved with the passage of time. So due to this, they are used on large scale, as well as wider range of temperature. Because as we said, membranes are mostly polymeric material. There are other membranes. Yesterday I told you that membrane are polymeric, as well as there can be ceramic, and sometimes they are formed of metals even. So polymeric membrane are most commonly used, which we have to discuss in next week. So initially, polymers, they can't sustain sometimes high temperature. Some polymers were developed which can sustain even high temperature. So they are now being used on large temperature range. They can be used for small temperature, for high temperature, as well as at high pressures. Because membrane material which you have developed, they have good strength. Also, when you compare these membrane to the other separation equipments, they have some other advantage. They can be used, or they have compact. They are more compact as compared to other systems, as well as they have less capital intensive, less capital cost as compared to other separation unit like distillation or absorption, etc. And they are more easily operated, controlled, and maintained. Their maintenance is easy as compared to those all other equipment. So control, all these are advantage of these membrane of these days, not old days. Old days membrane have problem, but now with the improvement in technology of membrane, these advantage are available as compared to other equipment. But they have one disadvantage, and that's the common disadvantage of membrane system, and that's need of parallel units. As I told you that we are using 4 parallel units inside the system which we have discussed just now. So why we were using those parallel units? You know that when we go for parallel units, definitely when you have to handle large capacity. So actually these membrane have some disadvantage as compared to other systems. Suppose if you look at distillation unit, absorption unit, LLE, so you can have one large equipment with various stages even inside that, but you don't go like for various parallel units. Large capacities can even be handled inside small systems. But when you look at this stuff, membrane, so they need parallel units in order to handle large flow rate. So I can't give you here the one number like large flow rate but if you look at various industrial process and capacities of membrane, you can get the idea. But one thing I can tell you, in this given process which we have discussed for this separation of hydrogen and methane, so in this all module they are of like surface area of each has surface area of 4000 feet square. So I mean overall you know that here it will be like 16,000 feet square surface area will be needed I mean for this separation. So this depends actually on the flow rates of the system in that define actually capacity of the plant. So if plant has a high capacity, so definitely maybe you are using membrane, so you have to use more than one unit. So this is one disadvantage. So other all they are advantageous as compared to some separation, but they can't be definitely used for all separation. So because membrane should be selective for the separation which you are looking for, but still they have many application these days, as I asked you to already go through the table 14.1 in the book. If you still didn't read it, just kindly go through that. I mean this is edition 4 of Cedar and Henley, and chapter 14 we are discussing these days. So just go through that table, and from that you can get the idea that these membrane are being used on wide scales in many industries. So this was all about the introduction of membrane. Up to here I'm just closing this lecture. Actually next topic is about membrane material, and that's due topic. We have to start with that in next week inshallah. So till now we have gone through the introduction, you know, basic terminologies of the membrane, and also now you are aware about the importance of membrane, that how advantageous they are and how they are being used, or where they can be used for separation inside in various industries. But here we have talked about one example. Thank you so much. So just go through this lecture, and if you have any question, just drop me an email or text. Thank you.